finally here I am alone. So, can anyone, before I introduce myself, can anyone recognize this object?
No.
We are not astronomers.
Supernova?
Not a supernova.
Black hole?
Nebula.
Yeah, nebula. So it's a picture of Orion Nebula that I took from my telescope at my home. So this has nothing to do with my project. I just gave it because it is a good picture. And okay, so the third language is Kannada. You will understand it. Why is Kannada? So here again a mesmerizing picture just to capture the audience attention. So what I worked with is actually lies here. The thing lies here. And here it is. So this is the region around the galactic coordinates LB 16.97 degrees and minus 1.031. So what it means is there is, like if you consider this as the galactic disk, B is the latitude and L is the longitude. So basically this region lies very close to the galactic disk where there is a lot of star formation. And do you find it interesting?
Yes.
Yes, no, maybe?
Yes.
No.
Let us find out. So, my name is Usman Chattopadhyay and I am a third year BSMS student. So, I did my project at the Indian Institute of Astrophysics, Bengaluru. And the original title of my project was a photometric analysis of an open cluster Dolidze 28. But it turned out to be the dilemma of Dolidze 28. How was it the dilemma? Let me show you. So the plan of today's talk is introduce what are clusters, what data did I use, and where do we find these objects in the literature, and rush to the theoretical things because we don't actually visualize them, it's just maths, and then finally conclude. Okay, so upon closely observing a good night sky, we can see some small faint smudgy patches of objects which stand out against a black background. And if you live in the northern hemisphere, and yes, we all live, except the Andromeda galaxy and Orion Nebula and clouds of course, these patches are called star clusters. Our galaxy contains numerous such agglomerations of stars. So again, if anyone is able to answer all these three objects, he will get a free treat from me in the basement. So can anyone of you identify these three objects? It's a little dim, but if you are
Light on.
Maybe that side.
Light off.
so let me tell the story behind this picture. So this was taken at the roof of our Niladitha hostel. I took this photo and it was processed by my friend Shantanu, who unfortunately couldn't make here today. So yes, can anyone of you identify these three objects?
It's not even visible. The bottom one looks like Pleiades a bit.
Yeah, that's correct.
Green one isn't visible.
Yeah. Now it's good. Yeah, latest tell is that.
Red is it Andromeda red?
Yeah, correct. Green one.
रोहन खिला मेरे को.
Guess now.
Should I tell?
No.
Yeah.
Give some hints.
It's again a galaxy.
Is it M51?
It has a common name.
Whirlpool?
No.
Century.
So any more chances?
No.
Well, this is the Triangulum galaxy, and these two are the only naked eye galaxies, and it should be naked eye. but we live in an unfortunate place, so it's not. And yes, so star cluster, yes, and this is the Pleiades open star cluster. So yes, star clusters are known since millennia because they are easy to spot and observe. And towards the end of the 19th century, as optical instruments become more superior, clusters were able to, we were able to segregate the cluster in two distinct categories. Some took a good spherical globe-like shape, while others had a ragtag open appearance, like this one. So as you might have already guessed, they are called globular and open clusters. So let us learn what are globular clusters. So globular clusters are actually the senior citizens of our galaxy. Why? Because they were formed only once in the galactic halos during the formation of galaxies themselves. And they are massive in size because they contain huge number of stars, about 10,000 to a million stars. And yes, and they are more luminous because they have more stars, and also because they are older, they contain many red and yellow stars. And also they contain weak absorption lines of metals. Now, to give a disclaimer, in astronomy, metals are anything heavier than helium. So, sorry TCS. So, why does it contain weak absorption lines of metals? This is because these stars were formed very early in the universal history, from those remnants of stars which didn't have any time to synthesize heavier elements. And yes, and this also has nothing to do with my project. Yeah. Finally comes open clusters. So what are open clusters? Open clusters arise from stellar association. So let's visualize this. Imagine you are standing in front of the sub-number gate and you are observing the road. And you see lots of bikes and scooters are moving all in the same direction, continuous, at the constant speed. Sooner or later, and if you are smart enough, you will see some of those bikes sort of clump together and go, while some tend to drift apart. This is exactly what happens with stellar associations, but on a large scale. Our sun is also thought to have begun life in some loose and long ago abundant association. Moving on. So I already said that they arose from a large, more diffuse association of stellar associations, and they began life, these opened from a single molecular cloud of gas. So molecular cloud of gas is a big gas of hydrogen. So when they start collapsing under, there is a weight called Jeans instability criterion. So after it is reached, they collapse and they form what are known as protostars. And all the open cluster stars are formed from a single cloud of gas. So which means they are all of the homogeneous nature. They have the same age, they all lie at the same distance, and they also have the same chemical composition. And they are also moving together in the space in the same direction. And unlike globular clusters, they continue to form today in the galactic disk. So let us see some of their features. Yes, open clusters are hot, young, blue and dynamic. They are less bright because they are obscured by gas and dust, and they have less stars. And they are metal rich because yes, they are still forming from the matter from the supernova remnants of massive stars which have already synthesized the heavier elements. So they are metal rich, and yes, as we have seen in the picture, they have a very diffuse morphology. So to give a sort of visual overview, all the globular clusters lie in the galactic halo and they are all orbiting like this, and all the open clusters are formed very near to the galactic disk. So mine cluster, why study open clusters? Why do we bother to study them? Let's see. They are, as I already told, they give a homogeneous samples, which means it is ideal to study these regions because you can understand how stars of different masses evolve together. And also we can study the effect of extinction. I will define what is extinction. That testing theories for theories of stellar evolution, dynamic environment. They are young and dynamic and unstable, thus they provide insight into high-speed stellar processes. And the most important part is we can extrapolate it to understand far away, massive, large-scale superstructures of galaxies, like the Saraswati supercluster, which you might have heard. So, what data did we use? So we use the data of primarily the Gaia satellite, which is a satellite launched by the European Space Agency, and yes, it looks like an UFO. We consider the 5 parameter astrometric solution. These are the alpha delta, the position coordinates, and these are the proper motion coordinates, like the Vx, Vy. These are the parallax, and these are the photometry, and these are the errors. And we sort of indirectly use the data of PUMA. So PUMA stands for 2 micron all sky survey. So it was an infrared survey conducted jointly by Chile and the United States. And PUMA is particularly useful because it primarily images in the infrared spectrum, which is very helpful because we can see the stars. We can see the stars as they are not obscured by the gas and dust. So infrared light can easily penetrate the gas and dust. So how do we use this? We see in the upcoming slides. So consider the wavelength band G. So wavelength band is specifically like a band of wavelengths and centered around, like it's a Gaussian and centered around the particular wavelength. So we have this equation where the first term is the apparent magnitude. This is absolute magnitude. Apparent magnitude is the brightness of a star that we see here on Earth, and absolute magnitude is the brightness that the star would possess if it were a distance of 10 parsec from the Earth. The term in the middle accounts for the fact that brighter objects grow dimmer as they are farther away. And the term factor 5 comes from the experimental observation that a 6th magnitude star is 100 times fainter than a magnitude 1 star. And the term in the last is extinction. What is extinction? Extinction just refers to the dimming of starlight due to interstellar dust. You see, space is not empty; it's filled. It's very filthy. So if this filthy dust were compressed to the density of air in G06, then I wouldn't be visible to Shivasiddha. So it's so filthy. And this is a photo of the famous Barnard 68 dark nebula. So dust not only dims, but it also reddens the light. We know from the Rayleigh scattering law that the scattering intensity is proportional to 1 over wavelength, lambda to the 4. So this means blue light which have lower wavelength are scattered highly and significantly, and so you can see the stars which are deeply embedded in this gas dust appear redder in color, which means the shorter wavelengths are all scattered away and leaving only the redder and the longer wavelengths. So if you see this this is a picture in visible light. If you see this in infrared light, you will see this region is full of stars. Yes, so mathematically defining, AG is nothing but the difference between the observed apparent magnitude that we see from the telescope and M0, which is a theoretical one, that would be observed in the absence of dust. And color excess or reddening is defined as difference between observed color and the intrinsic color. Intrinsic color is the one that would have been actually if there were no dust around in our line of sight. So EBPRT, so color is defined as, let's say, the difference in two wavelength bands. Like say if I take G, BP, RP, these are three wavelength bands. So you take any two of them, like GBP, GRP, or GBP, GRP. So these pairs are known as color. So you basically subtract the magnitude in these two wavelength bands. So EBPRP is ABP minus ARP. Okay. What is Dolidze 28 in literature? So I also didn't know this, but when I was preparing the PPT at IIA, just 2 weeks ago, I found that in 1960, the Soviet astronomer, Madonna something, he created a catalog of 57 open star clusters, and these are called Dolidze objects. And I found this in a very old Russian circular. Okay. After thoroughly reviewing the literature on this cluster, we discovered that all the recent studies are cited from either MWSC survey or the UCSC 5 catalog. What are these? So in MWSC survey, it was done by this person, again a Russian. He utilized two ground-based observations, 2 mass and MXL, and what they did was they already had a predefined data set of already studied clusters. And what they did was, for the suspected cluster candidates, they actually mapped their properties with that of the suspected candidates. Like they mapped their CMDs to those isochrones of already studied clusters. And on the other hand, UCSC 5 catalog again was a ground-based astrograph, which was again calibrated using APAS DR2 data. And keep in mind that it's also ground-based. And stars were considered in this catalog UCSC if and only if they are also present in the 2 mass observations. So an important thing to note is that both APAS and 2 mass were ground-based. So this means their observations were subjected to a very limiting magnitude of 12 to 40 magnitudes only. So if you recall, higher magnitudes means the stars are more fainter. So this means that these two catalogs cannot detect faint stars that are overglared in the galactic disk, and we will see a reason for this shortly. So observational study. So these are all the things we took. So we begin by taking data from the Gaia archive, did a cone search of radius this 0.25 arc degree, and these are the parallax cut and the signal to noise ratio for better parallax measurements. And these are the absolute, since we will later see that we will, to identify a cluster, we will sort of do a clustering on the velocity, proper motion velocity space. So what is proper motion? So in simple words, proper motion is just the shift of a star relative to the assumed stationary background stars. See, this is a picture of Barnard star, so it has the largest one proper motion. You see, in 1980 when the star was here, and in 2011 moved here. So this is known as a proper motion. So if you draw a vector in there, and you consider the sky as covered with grid lines like this, and this is the RA deck coordinate. You take its components, one is PM RA and one is PM deck. So these are actually these terms, and RUWE is like a parameter which tells that the data which we are actually working with is indeed a single star and not an unresolved binary. Okay. What do we do next? So we plot a vector motion diagram after a 3 sigma clipping. So what is 3 sigma clipping? Is just we have a histogram of the proper motion magnitude. We find its standard deviation. We find its median. We shift. Then we take. Suppose this is the median. We keep the data up till 3 sigma here and 3 sigma there, and we put the remaining data in trash. That's how it's done. So notice that some of these long randomly pointed blues like yellow, purple, red, so these are actually high proper motion foreground stars. So what actually happens is if this is a cluster, there will be some foreground stars in our line of sight, and since they are near Earth, they will have a higher proper motion because they have a higher parallax value, and there will be a lot of background stars. And moreover, the background star contamination is large specifically because this cluster is present deep inside the galactic disk, which are innumerable stars. They are filled with stars. This makes the study very challenging. And you see, even after doing a sigma clipping, we still can't find the the uniformity which is expected in an open cluster region. So what it should look in an open cluster is all the arrows will point in the same direction. So you see there are still very scattered arrows. So next what we do is we perform clustering on this proper motion space. So in clustering what we do is in x-axis there is PMRA and y-axis is PMDEC. So we do a scatter plot and then we do a clustering. So we use DB scan because if I do this, we'll get a cluster and we'll also get a field around it. So our data set will be segregated into a cluster and a field. And field is noise. And yes, and for the next analysis, we calculate the parallax values. We report the distance as this parsec, but so distance is obtained by inverting the parallax value. So when you are downloading the data, you have alpha, delta, PMRA, PMDEC, their errors. So it's all included in your data. So for the next analysis, we take the cluster center. We determine the cluster center by a Gaussian binning of the right ascension, declination, and the parallax. Now, what we got after DB scan is we got our preliminary cluster candidate. So now we would like to implement probabilistic models. So we just define this distributions, and these are this. It is what it is, and it is what they mean. The terms, this is sigma c, this is the formula, the intrinsic PM dispersion. And the important thing is this. So you see, this is the total distribution. So this phi I is actually the cluster part plus the fields part, which is the phi c plus phi a. So and they are normalized. So for each individual data point, we can find its probability p mu I by phi ci, this part divided by the total probability. So and yes, the 24 MS people, if you want to do this, you have to take maths. In the Somo sir will teach you the probability course in second year. That will be very helpful. And after this, we retain only those stars with the most probable candidate, which are probability. This probability is greater than 90%. We report 421 stars as most probable. Okay. So this is a plot of G versus GBPRP. This is known as the apparent color magnitude diagram of the cluster stars. I have plotted the data of these 421 stars, and this is the absolute color magnitude diagram. So this conversion capital N is defined by this term right here. And notice, keep in mind these purple points and these green points scattered. We will be using this later. Also notice the spread of the stars is too large. Like you can see a kiloparsec spread of the cluster, which is literally insane for a physical star cluster. So to ascertain whether it is consistent with other works in known open clusters, we perform a statistical validation, which is discussed in the further next section. We proceed to implement a technique called divide and rule. What do? We manually divide those main sequence, which are the violet regions, and the green clump of greenish points scattered. We separate out them, and for the whole data set, we calculate the parallax. We plot a histogram of the parallax, and we proceed to clip both these data sets between the first and the third quartile, which is the 27 percentile and the 75 percentile, because this is where statistically most of the distribution lies. And after clipping, we get the numbers as 136 and 42. Now, if I plot, let's say on y-axis, we plot. Is it visible?
No. Use your phone's flashlight.
Oh, my phone is there. So what we then do is, once we plot PM array, and then we plot PM depth, and these are the number of stars. Okay. So first we plot the histogram of proper motion for each of those categories. Let's say we are plotting for main sequence. We'll get a sort of histogram like this. Okay. And when I click both this data set, when I click this data set between the parallax, which means that I am spatially restricting my data points. So if it were really a cluster, remember all the cluster stars should have same proper motion, which means if I click the data set, the proper motion spread is expected to fall within a more concentrated region, like this. Let's see what happens. Yeah, PM velocities of most probably expect to fall in more concentrated region if it were really cluster members. But here is the funny part, we see it spread out over the same range as and before clipping. Yeah. So this is the original main sequence of this PM array, this PM depth, and this was the greenish points. You see that before clipping it was blue, and after clipping, spatially restricting also, it still spread over the same range. What this means? There is something fishy here. What can go wrong? So we consider possible explanation. The existing contamination of plots is arising due to the similar proper motion magnitude of background field star. So remember in the beginning we did the proper motion based clustering, in where we excluded the foreground stars. So now it so happens that in this region the background stars also have the same proper motion as that of cluster star. So they are coming together in the same data set, and they are eventually contaminating it. So how to remove it? We now resort to FSD. FSD is field star decontamination, and this was implemented by Dhanush Bhaiya at IISER. So I talked to him and we worked on it together. So I wanted to explain this in detail, but we have a time constraint. So briefly, what are you going to do is, I can do the talking. This is the most probable cluster candidate, and then we take field regions in these concentric circles such that the area of this entire concentric circle is equal to area of this circle. And what we do is we take each data point here and we iterate it through all the stars in these concentric circles and see if they have a matching photometric property. So, and if they have a match, and if they find a counterpart, we remove both of them. And if we don't find a counterpart in this concentric circle, we go to the next one and we proceed it. This is called FSD1, FSD2, FSD3 and so on. And at the end, what the data points, what we will get, that is the maximum that can be obtained statistically. So these are the steps in detail. I will use the Haversine formula. You can look at it. So, okay, the shocking thing again. After performing field star decontamination 3 times, we notice that the resulting cluster numbers are decreasing by half at each step, leaving us with 2 field stars at the end. So you see, these were before cleaning, and after cleaning 3 times it has shrunk to this. So this leads us to conclude that, what are you concluding? That a large fraction of our previously data sets, previously most probable candidates, are indeed showing the same properties as that of field regions. So this is a very big mystery, and also no special microclustering is observed in the radar Broad main series as well. So microclustering is basically that if you have all the stars of the same age, they will all lie in a single line, and in here what I get, I get many such lines. Which, what does it mean? This means that stars are not of the same age and hence not in a cluster, not in this open cluster. Finally, to conclude that, particularly owing to this Dolidze's position in the galaxy, there are enough reasons to conclude that it is an outlier in the mass scale automated surveys like MWSC and UCSC5 with no validation since. And magnitude limitations, as I previously pointed out, both these data sets, MWSC and UCSC catalog, they use data from ground-based observation, which means it cannot detect the faint stars. So what actually happened was that they actually misclassified those bright foreground objects which had high propagations before. You see that, if you remember, I actually removed those foreground stars at the very beginning, those which had long arrows. So they classified those as the cluster stars and they published their results. And star types is, and this is another shocking thing. So I tried to do a little experiment. What I did was I took the data from a nearby field region. Like I shifted 1 degree in array where there is no cluster. I took the data, and when I plotted those graphs, I was able to reproduce the same color magnitude and velocity point diagram as in my cluster case. So this is another evidence. Again, the significant amount of star loss in field star decontamination process proves that most of the cluster candidates are no less different than any other field region. To large extent, if you remember, I showed a plot where it was plotted depth versus distance. So stars were spread over kiloparsec. So this is clearly unphysical because you cannot have a bound system so big and so spread apart. If you recall that, I think upon solving the virial theorem, you can get specified like in a given area. You need to have a lower bound for the number of stars to be gravitationally bound. So that area is too large. But you see, the largest known open cluster is only 60 parsec, and this is about 2000 parsec spread. Also, if you want, I can also show you the visual evidence. You cannot identify by eyes any such cluster in either BSS, UMAS, Allwise or Pan-Star surveys. We try to determine a correlation between our results with Dolidze and Dolidze 28 for being an open cluster, but we find no proof of that. Henceforth, Dolidze 28 is not an open cluster, and the key takeaway is published results may not always be correct. So, to conclude, I would like to acknowledge a respected director of IIA and my guide, Kamath sir. And yes, thank you Gluon Club, DPS, for giving me this opportunity. These wonderful people, my colleagues, last but not least, my friends and comrades. And this work has made the use of ESS Gaia mission, SIMBAT database operated by CDS in Strasbourg, VCR online catalog and Python. Thank you. Any question? And yes,
Is the all data that are publicly available?
yeah, I mentioned like if you search Gaia DRT archive, you will get a page of ESA. You open that and you select a query. There is a tab called query, and there you search for like single object query. You need to put SQL commands to extract the data.
One question. Do you have any idea how these surveys classify clusters? Like what's their algorithm like?
Yeah, these actually surveys, they use artificial neural networks to that these are automated large scale surveys. So what they do is they literally take the whole sky, they put clustering algorithms and they dump them into supercomputer and they publish the results.
No, like this algorithm that they use, is it based on machine learning or is
Machine
it some
learning.
sort of an?
Now what they're doing is entirely based on machine learning. And this work is significant because earlier all the catalogs were before Gaia mission, and Gaia is significant because it provided for the first time the position and the velocity. And earlier they only used the photometric component like the lights. They only classified cluster from just by seeing their lights. So this is a big milestone. And
So one remark that right now there are like these pipelines for tests as well. What they do over there is they make TOI, test object of interest, and they don't classify something as hosting an exoplanet or not.
yeah.
So these guys, like their pipeline spits out that it is indeed a cluster or it's a cluster candidate.
No, like what they do is they give a bunch of data
Huh.
and they train their model on previous studied data.
No, that's not what I'm asking.
Ah,
So the output that they give,
yes.
if they identify certain group of stars as a cluster,
Ah.
do they say that it's indeed a cluster or it's a cluster
So
candidate?
if they give, like say in one model they give like it is a cluster, it might be a cluster, it
Okay.
might not be a cluster, and it is not a cluster.
Okay.
So they separate it down into four
Okay,
categories
okay.
like this.
And they identify it as it is a cluster.
Yeah.
Okay. Using Gaia,
No.
not using Gaia.
Before
okay.
Gaia.
Okay.
Before
Because
Gaia-
they didn't have the position like
Yeah,
velocity.
because Gaia gave the position and those velocity measurements, and these are the most important things that are crucial to understand open cluster. You can't just see the light and
Yes.
give your thoughts. Any other?
Amazing presentation.
Thank you.